So welcome everybody. In this video, we're going to present our project that it was the autonomous C1 Ackermann SAC-based dynamic obstacle evasion on a scale F1 Imola circuit. Well, in the first video, we're going to present the evidence of the PID controller working. With the PID, we just needed to use the trajectory tracking and for the Ackermann to make the path following of the complete track. We can see that it has no problem of doing the predefined trajectory. For the same case, we use the RL for the trajectory tracking. We see that even though it's a little bit harder, well, the Ackermann is completely trained to make the trajectory tracking in a correct manner, and it doesn't matter if it has curves or so has to make difficult decisions or turns. The Ackermann is doing the trajectory really nice. Well, this is the evidence of the PID obstacle avoidance. We can see how the Ackermann is can avoid either obstacle from the right or well, we're gonna see in the next video that it can also avoid from the left, but in this PID is from just avoided both the teleporter and the autonomous robot. And finally, this is the evidence of the RL obstacle avoidance. We can see that the Ackermann is avoiding with success the autonomous car, and he avoided the car from the right, and now he's gonna avoid the teleoperated from the left. Now we're gonna continue with the evidences, but this is the physical evidences that our project was successful.
Okay, so here we have the four experiments of the project. In the top part, we have the track following between the PID and the RL. They are they achieve almost the same results just for track following, and the important part is the obstacle avoidance. The differences between these two is that the RL has less error, but the PID, in the other hand, it has more repeatability. So that's why we consider the PID is a better choice. And also, in general, the success rate we will see it later. It is bigger in the PID. And so we have the videos and also the graphs showing the error to know if the Ackerman is following properly or not the path.
In conclusion, after completing 4 experimental runs across trajectory tracking and moving obstacle scenarios, we successfully validated both the classical PID controller and the SAC-based reinforcement learning controller on a real Ackermann platform. The result shows that PID achieved the best nominal tracking performance, reaching a 100% tracking success rate without obstacles. However, when dynamic obstacles were introduced, the SAC agent maintained an 80% tracking success rate and demonstrated better trajectory recovery after evasive maneuvers, reducing RMS tracking error and maximum deviation compared to PID. Additionally, all evaluated groups achieved 100% safety success, meaning no collisions, no safety ratings violations, and no emergency stops were recorded throughout the experiments. The results suggest that while classical control remains highly effective for structured trajectory following tasks, reinforcement learning provides great adaptability when the vehicle must react to disturbances and recover from unexpected situations. Finally, we identified several opportunities for future work, including improving obstacle evasion consistency, reducing the scene-to-real gap, and increasing linear relationships on to unseen environments and obstacle configurations.